Hello and welcome to Cup of Cosmology, the place for all your questions about the universe. My name is Diana Hooper and I'm a postdoctoral researcher currently at the University of Helsinki in the Helsinki Institute of Physics over in Finland. And I study cosmology. So that means that I study the universe, the contents of the universe, how everything evolves, how everything interacts, basically all of the fun things happening inside the universe. I love studying cosmology. It's a really, really fun topic. There's just so much you can study with cosmology. Everything from the first fractions of a second of the universe to the eventual fate of the universe and everything in between. So I love being a cosmologist. I love being a scientist. And I really like chatting to people about all of the cool things happening outside or in space, all of the cool things I get to study. Hey, David Howden, Scott, David Dunn, Paul Hess, great to see you all, the core followers coming in. Great to see the regulars here as always, and welcome to anybody new. So yeah, I love chatting about science and space and physics and everything cool that I get to work on and academia and in general. I just like chatting to people. So Cup of Cosmology is a place where I get to chat to everybody about all the fun things that I enjoy chatting about. And you all get to ask questions about whatever you've ever wanted to know about science, cosmology, academia, me. Any questions are welcome. So I don't have a topic today, but as always, this is an interactive stream. So the idea here is that you can ask me anything you want, and I will do my best to answer. Hey, James, great to see you as well. Great to have great to have all of the regulars in here again. I'm going to start with a disclaimer that I'm not sure if we're going to do a 1 hour stream today. As you can probably hear from my voice, I was sick last weekend. I'm feeling better. I'm fine, mostly. But I completely lost my voice and I spent the whole week barely able to talk, which has been fun, especially when I had to teach. But my voice is coming back. But I am not sure if my voice will survive a whole hour of stream. So we might be cutting it early today. That said, I know there's a high chance that I will just go on for an hour regardless. But just as a warning that I might have to cut the stream short today. And as David Dunn is saying here in the comments, if you like Cup of Cosmology, please do like the video, subscribe, leave a comment down below. Do all of the usual stuff you do on YouTube. It really helps increase engagement. I recently, a few days ago, I just passed 5,000 views on YouTube, which is an arbitrary milestone that I find pleasant. So thank you to everyone who's helped make that happen. It's really nice to see so many people engaging with my content. So yeah, please do like, leave a comment, subscribe, do all of the usual stuff. If you're watching on Twitter, that's awesome. For now, the stream is still going out to Twitter as long as Twitter's around. If you want to join the conversation, please do head over to YouTube. Hey Keith, hey Ange, great to see you too as well. Yeah, speaking is overrated. I would agree, except when I'm trying to do a live stream where the purpose is me speaking, in which case speaking then becomes a necessity. But yes, speaking in general, we all speak a bit too much anyway. We should all listen more and speak less. So on the note of what I just said about Twitter still working for now, currently, anytime there's an announcement for Cup of Cosmology, like a guest or the link to the YouTube stream or a change in schedule, I'm posting this on Twitter. Now, there is a chance that Twitter might not be viable long term. So, oh, you post my shows on Facebook to get people to join in. Thank you, Keith. That's really kind of you. You know, I used to be on Facebook and I moved off of Facebook long ago, but thank you for promoting the show and getting more people in. Always happy to have more people coming in to watch. So, yeah, I'm glad that somebody was amused at my phrasing about the 5,000 miles. Thank you. 5,000 views. Thank you, Scott. God, I'm going to be singing 500 miles all day now. My brain is jumping around a lot today. Anyway, in the event that Twitter is no longer a viable option, I am going to move updates from Cup of Cosmology somewhere else. And I'm not yet sure where this somewhere else is. So one option that I'm toying with and that I think a lot of people reacted positively to is setting up a Cup of Cosmology Discord server. So for anyone who hasn't used Discord, Discord is very similar to Slack. You have different channels, you have a server around an idea, you have different channels, and you can all chat to each other. Now, a big advantage of having a Cup of Cosmology Discord is there could be side conversations apart from just the show. You could ask questions, you could discuss among yourselves, you could pitch ideas for the show. It would be really a place for the community to come together. That said, I can see that having a Discord server would be a huge amount of work for me and it would immediately become a time sink. But I am very open to the idea of setting up a Cup of Cosmology Discord server if there's enough interest. Although from the Twitter poll I did, it does seem that people tend to prefer the idea of an old-fashioned newsletter much more than Discord. That's also an option I'm considering. If you haven't yet voted on my Twitter poll asking what to do with Cup of Cosmology updates if Twitter's no longer around, you can still find it. The poll is still active for another 2 hours. It is pinned to my Twitter profile. So if you haven't yet voted in the poll about where to get future updates of Cup of Cosmology, please do go and vote in that because that will influence what I do. I might just ignore the poll anyway because this is not a democracy, unfortunately. And then I will just go ahead and set up a Discord server, but we'll see. But please do feel free to go and vote in the poll if you haven't done so already, and then you can help decide. As for the people saying Mastodon, I'm going to put this as delicately as I can. I am not a fan of Mastodon. I think Mastodon is very much not the place for me. I have no intention of creating a Mastodon account or joining any of the many Mastodon servers out there. If people are finding a new home there, great, have fun. I hope you will enjoy it. Personally, I am staying well away from Mastodon. So no, that is not an option. That is not going to be an option in the foreseeable future either. But thank you for the suggestion. I knew somebody was going to mention Mastodon, so thank you for that, but not going to happen. Okay, so a few comments and stuff aside, let's actually get into physics. And I saw there was a comment by James earlier saying the grand unified theory explained today. Well, that is certainly a big topic that one could discuss. So I'm making a note of that, and I will come back to that in a minute because I just saw, James, you had another question. So let's jump into that other question as well. Just checking that I didn't miss any other comments. No, I did not. Okay, so another question from James. I heard that black holes eventually evaporate, but in this process, they will eventually explode. And it's moving away. Not sure why evaporation of its matter would cause an explosion. Okay, so this is a great question there, David. So Macedon gets a point against it just for the name. Yes. Yes, I am not going to rant about Macedon. I am not going to do it. Not here, not today. So a black hole is a region of space-time that is so dense that nothing can escape, not even light. You'd need to be traveling faster than light in a vacuum in order to escape the gravitational pull of a black hole. As far as we know, nothing can travel faster than light in a vacuum. Therefore, nothing can escape a black hole. And there are several different ways black holes can form. One of them is the most common one we think of. When a star reaches the end of its lifetime, it collapses. During this collapse, it explodes and it forms a black hole. Another potential way you can form a black hole is in the early universe. If you have a region of space-time that is really, really dense, it can directly collapse into a black hole without going through the whole star stage. Now, there is something that can happen around black holes that is really cool, which is... Yeah, thank you for that, Scott. I'm still going to be definitely going to be singing that song even more now. Yes, once 500 miles sticks in my head, I'm going to spend the whole day like, and I would walk 500 miles. But yes, we're not doing that today. This is not a karaoke. Although Cup of Cosmology karaoke would be very fun. Pinning that for the future. Okay, so you can have a cool process known as Hawking evaporation. So in the universe, you can have particles and antiparticles spontaneously created from the vacuum. So what happens here is you kind of borrow energy from the universe. You create a particle and an antiparticle, and these immediately annihilate because matter and antimatter annihilate. So they immediately annihilate and give back the energy that they've borrowed from the vacuum. Now, if this happens on the event horizon or very, very, very close to the event horizon of a black hole, what can happen is that you could produce particle and antiparticle. One gets sucked into the black hole and the other goes away. So here we're not talking about a particle leaving the black hole itself. There are a pair of particles that are created just on the event horizon, and they're created with enough energy that one can fall in and one goes out. Now, at this point, you can't pay back the energy that you've borrowed from the vacuum, but energy must be conserved. So the way we get around this is the black hole actually loses a bit of mass. So the black hole loses a bit of mass and a particle escapes. But this is not saying the particle has escaped the black hole, but rather two particles, a particle and antiparticle, were created on the event horizon. One went in, one went out. And then the black hole loses mass to compensate the creation of this particle. So when we say black holes are evaporating, what we actually mean is that they're having this pair production of particles, and one is escaping, one is falling in. And this is what we call Hawking radiation. Now, over the years, many billions of years, these black holes are gradually going to get smaller and smaller and smaller due to the loss of mass. At this point, once you start condensing it smaller and smaller and smaller, at some point you're going to have the problem that there's just too much contained there. Then there's a question of what happens to the information that is contained within a black hole. So information is everything from energy to just knowledge about a state. And technically, this is something that cannot be destroyed or created in the universe. So if all of the information falls into a black hole and at some point you can't contain this, it will explode. This could, for an example, produce a high energy gamma ray burst or a highly energetic burst of energy. Now, we are getting into the realm of this is difficult to describe mathematically because the whole process of Hawking evaporation and these black holes evaporating would take billions and billions of years, which means if the typical black holes that we think of, like stars, if these are stars that have collapsed, if these undergo Hawking evaporation, it would take billions and billions of years for them to actually reach this stage of producing the gamma ray burst. And it would take longer than the time since the first stars have formed. So it's not something that we think has happened yet. However, if we consider primordial black holes, the ones that were formed in the very, very early universe, now these could actually already have undergone Hawking evaporation. So then what we can do is we can look for signs of these highly energetic bursts and see if we can trace any of them to a potential primordial black hole. Currently, we have not been able to do so. We have not found this clear link. So would an evaporating primordial black hole actually have this end explosion? It depends on what happens to the information contained within the black hole, which we don't know. So it's a very difficult question to answer. It's a very good question, James. But yes, you can have this Hawking evaporation, and this could potentially result in an explosion, or more of an explosion like a burst of energy. So that's very, very cool to think about. Let me just see if I definitely missed some comments. I stopped on one comment and then missed all the ones coming afterwards. Are early universe black holes formed before, during, or after inflation? That is a great question there, Paul. So I see a lot of you like the idea of karaoke and are singing along in the comments, so that's fun. So if yes, and I just saw Scott's comment about talk about information overload. Haha, yes, indeed. So, are early universe black holes formed before, during, or after inflation? We're not sure. Probably after. Most likely after. Because the cool thing about inflation, so inflation is this period in the early universe where the universe grew exponentially. Everything was pushed very far away from everything else. Inflation erases the memory of anything that came before. It is such a dramatic process that it could have lasted billions of years. Inflation basically resets everything we know about the universe. So if primordial black holes were formed beforehand, we wouldn't see them today. Now, one of the main ideas for these primordial black holes is during inflation. This is something we discussed in a stream a few weeks ago when I had a guest on, Lorenzo. During inflation, because everything is being stretched, any quantum fluctuation or any vibration or any wavelength in the universe is also stretched. So this means that you can go from a very early tiny universe where you have just quantum fluctuations, which are just things vibrating in the vacuum. And if you stretch these during inflation, you actually set the seeds to form what we call overdense and underdense regions. So regions where there's more density in the universe and regions where there's less density. This can come because of this rapid expansion in the early universe. So at this point, it seems likely that these overdensities, which could then collapse into primordial black holes, could have formed after inflation. And in fact, a lot of people work on the idea of what if inflation itself directly produces the formation of primordial black holes. And then you can look for signs or different things related to primordial holes and use that to constrain the physics of inflation. So in the scenario that we usually think of, a primordial black hole forms after inflation and sometimes because of inflation. So we usually place it afterwards, but then you could also argue that is this still part of inflation? So does it form during inflation? But usually we consider if primordial black holes formed at all, because we're not sure if they did. But if they did, it was probably after inflation. Okay, there was another comment by Keith earlier. I know I've missed some comments. People are going really quickly today. That is fine. Keep them coming. I will catch up at some point. I will catch up with all the comments, so do keep them coming. There was a comment by Keith there of which came first, black holes or galaxies. And I love this question. One, because it's a very cool physics question. And two, because it allows me to make the joke that I've made a couple of times on the show now about what came first, the chicken or the egg? Well, which one did we name first, or which linguistically came first, which may or may not be more important. So in that regard, we named galaxies first. So linguistically, galaxies came before black holes, but we're not going to have that debate. So from a physics point of view, which came first, black holes or galaxies? That is an excellent question that we do not have the answer to. Now, let me add some caveats here. If we're talking about black holes coming from collapsing stars, this could happen before galaxies. All you need is a star. For a galaxy, you need a bunch of stars. So you could have individual black holes before galaxies themselves, especially if you want to talk about primordial black holes. Primordial black holes were formed long before galaxies even existed, before the first stars even existed. Now, if you want if you want to ask the question about supermassive black holes, then the answer changes. Tea is still too hot. So supermassive black holes are black holes that are at the center of every galaxy. And supermassive black holes, when we think of a black hole like the stellar mass black holes that we call them, they're a couple of times the mass of the sun, maybe 30 times the mass of the sun, maybe 50. Supermassive black holes are billions of times the mass of the sun. So they're like you take billions of suns and you collapse them into a black hole, and this is what we call a supermassive black hole. We know that at the center of every galaxy there is a supermassive black hole. We're not yet sure if the galaxy formed, and as a consequence of the galaxy forming, the supermassive black hole formed, or if the supermassive black hole formed and the accretion disk, or the matter swirling around it, then triggered the formation of galaxy. So your question is a very interesting question there, Keith, and breaking it down, primordial black holes came before galaxies. Stellar black holes, more or less same time as galaxies. Supermassive black holes, we have no idea if they came before or after galaxies. We're still trying to figure that one out. Okay, a cup of karaoke, yes, people singing here. Question from David Howden. If inflation involves space-time itself expanding faster than light, which is true, could something like that happen inside a black hole and let something escape? Now, this is an excellent question. We know that in the early universe, inflation did happen faster than the speed of light in a vacuum because there are no such restrictions on the speed of space-time itself. Now, in order for this to happen inside a black hole, we would need to ask the question of what is inside the black hole that is causing this. So when we're talking about inflation, we often talk about some field that is inflating, but inside a black hole, the problem is all of our physics break down, all of our maths breaks down. We have no idea what happens inside a black hole. Now, going with our idea that space-time inside a black hole is basically something we cannot describe, beyond the event horizon, we have what we call a singularity, which means our equations break down. We cannot describe what happens to space-time inside a black hole. Now, if you've seen before the analogy of a grid drawn, like grid lines drawn on a planet warping space-time, when you put a black hole there, often it just goes down. Like we break space-time at that point because our equations break and we don't know how to compute it. So at that point, we can't describe space-time inside of a black hole. So in order to make it expand, we'd first have to be able to describe it, and we can't. So mathematically, it's not something we can answer. Now, physically, we would need something inside the black hole that could trigger inflation. And as we don't know what exactly triggered inflation the first time round, that's quite a difficult question to answer. Now, going back to the idea about inflation making things expand faster than the speed of light, there is the caveat that in the early universe, it was very, very, very small. So reaching this threshold of something moving a specific distance in a specific time is much easier in a small space. But once you have something very big like the universe today, it becomes conceptually a lot harder to reach this threshold of forcing space-time to expand that fast. So it's a very, very interesting question, and one that mathematically is difficult to answer and physically is difficult to answer. And I love those questions. Okay, let's see. I know I've missed some questions there. Let me catch up with them. Not every galaxy, those pesky ring galaxies don't have one. That is true, Scott. There are occasional galaxies that we have found that don't seem to have supermassive black holes. Those are fun. Those are difficult, but in principle, almost every galaxy, except for some caveats, has a supermassive black hole at the center. So, Keith, you have this idea of invisible holographic principle of the multiverse. I know you've put a comment on my other streams about that. As I said before, I'm not an expert in holography, so I can't really address that point. But yeah, we did have an expert on holography. There was a stream, one of my favorite streams with an expert on holography, where we went in detail about all of that. So I won't go into detail about that again. And I think, unless I missed something, I do think I caught up with all the comments, except the one by James earlier about grand unified theories. So let's jump into that. So what is a grand unified theory? Well, first let's talk about forces. Everything we know of, let's recap. As far as we know, in the universe, there are 4 forces. So forces are basically the way that things can talk to each other in the universe, so the way particles interact. When I say something interacts with light, it means it can exchange forces with one of the particles of light, which is a photon. So there are 4 forces that we know of in the universe, 4 ways that particles can talk to each other. There is the electromagnetic force. This is the one we're all used to. You know, you have a got my forces mixed up. Let's do that again. I always start in a different order, so I went autopilot kicked in. As far as we know, there are 4 forces in the universe. The first one is the electromagnetic force. This is one we're very used to. We have electricity, we have magnetism. I can turn on a light bulb, I can stick a magnet in my fridge. That's the electromagnetic force, electricity and magnetism. We used to think these were 2 separate things, but we realized at some point that we can describe electricity and magnetism as the same force. They're 2 sides of the same coin. Well, actually 2 parts of the electromagnetic wave. Electric wave, magnetic wave. They vibrate in perpendicular directions. In case you wonder what my hands are doing, they sometimes help. Sometimes they're just hand wavy. My hands are hand wavy. Anyway, electromagnetic force. We're used to this one: electricity, magnetism. Another force we have in the universe is gravity. Gravity is what keeps us in orbit around the sun. It's what keeps everything moving within the universe. Gravity is the one that lets me do that and let the pen fall down. Gravity, we think we have a pretty good understanding of gravity, we think. And then we have the 2 nuclear forces, the strong nuclear force and the weak nuclear force. The strong nuclear force is the one responsible for holding quarks together inside protons and neutrons, and it's also the one responsible for holding protons and neutrons together inside nucleus. Strong force is the one that glues everything together. And then we have the weak force, which is responsible for radioactive decay and a few other things similar to that. And there's one of these forces that we do not understand, and that is the weak force. I know you might all think, sorry, that is gravity. My mind is scattered today. I know from my explanation, you might all think like weak force is the one we don't understand. It's not true. Weak force we understand, strong force we understand, electromagnetic we understand. Gravity, gravity, we're still trying to figure that one out. Now, the reason that gravity is so confusing is that for all of the other forces, we have a particle that carries the force. When we're talking about electromagnetism, we have the photon. Photons are particles of light. They're responsible for carrying around the electromagnetic force. When we're talking about the weak force, we have the W and Z bosons. These are the bosons, the particles that carry around the weak force. And when we're talking about the strong force, which glues everything together, the particle we have is the gluon, because we are great at naming things. The gluon is responsible for gluing things together. It carries the strong force. However, for gravity, we're not sure if there's a particle or not. There's a hypothetical particle. We put a placeholder called the graviton, but we're not really sure how gravity works on the quantum scale. Gravity is really good at explaining things on large scales like the motion of planets, the motion of galaxies. But when you go down to the tiny, tiny, tiny particle world, putting gravity together is really difficult. So that is a problem we have. But the question was about grand unified theory. So just recapping, we have 4 forces, 3 we understand pretty well. Gravity, we're still trying to figure it out. In Einstein's general relativity, gravity is the curvature of space-time. However, you could still have gravitons involved. If you just describe gravity as the curvature of space-time, then it becomes harder to see how this really reacts in the way of putting it together with other forces. So gravity is both a force and the curvature of space-time. Question from Nadia here. Is the asymmetry between matter and antimatter in the weak force? Let me think about this. I want to say yes, but I also want to think about this. So we know that in the early universe, there was more matter than antimatter created. Every antimatter that could find a corresponding matter particle annihilated, produced a bath of photons, and there was a leftover bit of matter. So we know that in the early universe, there was more matter than antimatter. We're not yet sure what caused this, so we don't know why there was more matter than antimatter. We're still trying to figure that one out. That is known as the Paleogenesis or Electrogenesis, depends who you ask. So I would say that yes, it's basically a question of what happened. We're not really sure what caused the asymmetry between matter and antimatter, but that is a great question. Photons and electromagnetism, sleeping in past classes, these are linked. Yes. Photons are just the particles that carry the electromagnetic force. So I'm seeing a lot of comments in here, just going back to this. So yes, photons are just the particles that carry around the electromagnetic force. When you turn on a light, you get photons coming out. If you want to create a current, you need some type of photons moving around. So you really do, and electrons moving around as well with the, yeah. But the electromagnetic force, or especially the light part, is carried in the form of photons. So anytime you have an interaction that involves light, you have a photon at play. So the electromagnetic force is carried by the photons. So 4 forces. We have 3 that we have a pretty good understanding on. Gravity, we're still trying to figure it out. And I said before that we used to think electricity and magnetism may have been separate, and then we realized that actually they're the same force and are described the same way. Now here's where things get cool. When we go to very high energies, the electromagnetic force and the weak force can actually be joined together as an electroweak force. Oh, the reason this is important is because if we think of the history of the universe has gradually been getting colder and colder and colder as it gets bigger and bigger and bigger. This means that the universe has been getting less energetic. In the very, very, very early universe, everything had more energy, and now it's gradually dissipating throughout the universe. So the energy is lower. So when we talk about the history of the universe, if we're cosmologists, we talk about redshift, which is how much light has been stretched based on the expansion of the universe. But if you do particle physics, you talk more about the energy scales of the universe. What was the energy when specific things happened? This means that if you go further and further back in time in the history of the universe, you get more and more energy. So if I say that at high enough energy, electromagnetism and the weak force are linked, we know this because based on what we've been able to observe in the universe, we know that in the early universe, electricity and electromagnetic force and weak forces had to be linked, and at some point they broke apart. So at some point we had the electroweak force, and as the universe cooled down, these broke apart into electromagnetic force and weak force. But we did have this unification of electromagnetic force and weak force. This breaking away is what we call the electroweak symmetry breaking. And this is very, very interesting when we talk about things like phase transitions that trigger gravitational waves, which is what I'm working on today. So you might have heard me mention this at some point. So electroweak force is something that we know happened, and we know there was this breaking of electromagnetism and weak force going separately. So then we can ask a question: if at high enough energies, if at high enough energy, electromagnetism and weak force were united, can we do something similar with the other forces? And we're hoping that the answer is yes. So then, if you want to throw the strong force in, you'd have to go to even earlier times, even higher energies. And once you try to unite electroweak force with the strong force, that's where you get a grand unified theory. This is known as GUT, and the GUT scale is one that we cannot actually probe in the universe. So the electroweak scale, we've been able to do studies about the electroweak force. But the GUT scale, the grand unified theory scale, is the energy that you need to combine the strong force together with the electroweak forces. This is what we would call a grand unified theory. We're still trying to figure out if that works, how that works, when that worked. Work in progress, but it's a very interesting idea. So the idea of a grand unified theory is uniting strong force with electroweak. And now you can ask, what if we want to throw gravity in? Then we need a theory of quantum gravity in order to understand how gravity fits together with the others. And then we would need a theory of everything, TOE, aptly named theory of everything, which would be the theory uniting the four forces. So in our ideal scenario, in the very early universe, you had a theory of everything, then you had GUT, then you had electroweak, and then you had the four forces. But for now, we're stuck at trying to figure out GUT and theory of everything. So grand unified theory is putting the forces together in the early universe. I hope that answers the question of, are we going to hear about guts and toes today? We did indeed hear about guts and toes, about grand unified theories and the theory of everything. And David Howden is asking the follow-up question here about what about a fifth force, flavor force, which is one of the ideas suggested to explain some of the odd muon results from the LHC. So that is a very good question. For now, we've only been able to find four forces. There are a lot of hypotheses around fifth forces, either to explain dark energy or to explain inflation or to explain some of the weird things happening at the Large Hadron Collider. But for now, we only have four. Realize I should drink my tea because that also does help with my voice. So for now, we're stuck at four that we've been able to confirm. A fifth force would be very interesting, and figuring out how a fifth force works with the other forces would be very interesting as well. But first, we need to actually find a fifth force. So we're still trying to figure out how our existing Lego pieces fit together. Then if we find more Lego pieces, it becomes a bigger problem. So are there problems in quantum physics specific to either force? I'm not completely sure what you mean by that question. There are problems we can ask about all forces, like electromagnetism, we're okay with that one. But with the weak force, with the strong force, we do have different issues, mainly like the energy scales and stuff like that. But if your question is how do we unite gravity with the quantum world, that the problem there is that we can only explain gravity on really large scales. And when you break it down to very, very small things, that's where the problem is. So the problem in quantum gravity is more with the gravity than the quantum part, or it's really putting the two together, fusing them both. But there are problems with each force as well. Like with gravity, we're still trying to figure out if gravitons are a thing. So we do have these other issues as well. But overall, we have pretty good understanding of the forces. Okay, so there were a bunch of comments that came in while I was talking about grand unified theory. So grand unified theory is a grand topic, as the name implies. So, and I didn't prepare for that topic at all. So if you didn't catch my explanation, that's perfectly fine. Feel free to ask, let me know. We can go through it again. And maybe I can find an expert who works on these things to come and chat about that as well. Okay, let me just catch up on comments briefly and then go back to other questions. I know there was a question by Paul about dark matter. I am going to come back to that. I just want to carry on with grand unified theory first of all. Keith, you're currently in the process of building a photographic portal model. Interesting. That will definitely be interesting when you want to finish that model. More questions here. Let me see. The universe must have been pretty hot in the early days. Yeah, in the very early days, the universe was billions of degrees Celsius and very hot. Very, 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 very hot early universe. Okay, question about black holes. I'll come back to that. Let me just go through the comments, make sure I didn't miss anything here. I'm completely ignoring the reference to midichlorians because midichlorians should not have been a thing. but they are. So unfortunately, yes. Yeah, midichlorians, why did they decide that? We had the Force in Star Wars. We didn't need an explanation for the Force, and suddenly you had midichlorians. Anyway, yeah, well, nonsense. Yeah, quantum mechanics and general relativity just don't get on. I agree, they just don't get on. Okay, so there was a question from Ben about non-rotating black holes, and there's a question by Paul about dark matter. I'm going to take the non-rotating black holes one first. If non-rotating black holes have basically zero volume, would it be possible for something the size of an atom to contain another universe? Oh, this is an excellent question, and you can basically ask the question of how small can you make a black hole? Again, it comes down to the problem of how you compact stuff together, but there's no limit on you can have black holes that are so small they could actually zip through you without being noticed. So you can have tiny, tiny, tiny black holes. As to whether these could contain another universe, again, we get into the problem here that we don't know what happens inside a black hole. So I'm actually going to use the prop that I realize I have at hand and haven't used yet. So imagine this is my black hole, right? This is a nice little black hole with an accretion disk around it, matter spiraling around my nice plushy black hole here. So once you cross the event horizon, once you've gone in Mr. Plushy here, nothing can escape. So if there's another universe contained within this, it is out of reach. We cannot get any information about it. So yes, you could shrink. You could have a black hole that is literally this size. You could have a black hole that is tiny. There was actually one paper that became quite famous for a very illustrative plot where they're talking about tiny black holes. And on one page, there's a black circle printed, and the caption says, if you printed this paper on A4, this is a to-scale representation of the black hole I'm talking about, which is really cool that they actually did that. Yeah, I can't even remember the paper or the authors. I just remember that figure. So you can have tiny, tiny black holes. You can have plushy-sized black holes, or you can have big black holes. As to whether there's a whole universe inside them, that is very much a cool trope in sci-fi, but unfortunately, it's not one we can actually discuss physically or mathematically. Was that plushie connected to a white hole? Yes. So black hole on one side, white hole on the other side. You get the like snarky black hole, or you get the happy white hole. As you can tell by the logo, this is my latest Couscous Act merch. Couscous Act is the second best YouTube channel out there, next to mine, obviously. Couscous Act is an amazing YouTube channel. They do a lot of science outreach in really, really cool videos with amazing animations. And once a year, I buy merch from them to support their YouTube show. And they have a plushy black hole connected to a white hole. So how could I not buy my little black hole here? And it's sat on my desk, so it's a perfect prop. Anytime someone asks about black hole, I have a prop. And yes, I'm ignoring I'm ignoring all the comments about midichlorians because yes, I've already ranted about that once. Just keeping the midichlorian references going, you go ahead, I'm going to ignore them. So going back to the question quite some time ago by Paul. Any recent studies, news that makes different kinds of dark matter more or less likely or rules things out? Unfortunately, nothing hugely dramatic. So black hole research is slow going, and the thing about science in general is we rarely have these eureka moments. These eureka moments are great when there's a big new discovery, but usually science is a slow and gradual progress of updating models, updating theories, gradually progressing, ruling things out. It's very difficult to wake up one day and say, we've ruled out a whole class of dark matter models. Happens very occasionally where people come up with new experiments or new ways of doing things. And it's like, hey, look, we can rule out this thing that we couldn't rule out before. But usually it's just gradual progress, right? And at which point do you say a model is ruled out? Because you can often tweak the model to get it to hide. You can say, like, we haven't found it yet. I can give the example of something that I've worked on a lot is the idea that dark matter could interact via a very, very, very small charge with photons. So we say that dark matter doesn't interact with light, but then I've asked the question in some of my research papers of what if it does just very, very, very lightly. And the answer we can give is, well, if it interacts, the interaction strength has to be smaller than something. And the more data we get, that smaller than something becomes. So then at which point do we rule out that possibility? Do we just keep pushing it smaller and smaller? At which point do we say this is no longer a good option? And this is the thing, that it's very difficult to rule things out. Now, the easiest way to rule things out would be with a clear prediction that is falsifiable. For an example, if I cook up a dark matter model that produces gravitational waves, there are models that do this. So imagine I come up with a model and say, okay, this dark matter model produces this amount of gravitational waves. If we do not see this amount of gravitational waves, this dark matter model doesn't work. Then we build LISA, we send LISA to space, it looks for gravitational waves, it doesn't measure these. Then we say, like, okay, this dark matter model didn't work. So there are thousands of dark matter models on the market. Every day there's probably a paper that narrows it down a bit more and narrows it down a bit more. But ruling it out is hard. Unless there's a clear prediction that doesn't work, it's very difficult to rule it out. So there is still research being done on dark matter, and it's amazing research and it's really fun. And I check the science papers every day, and every day there's papers like, we're pushing the boundaries slightly smaller. There's less space where dark matter can hide, but we still haven't found it. So there's been, as far as I know, no big news, no big breakthroughs in terms of dark matter in the last month or so. But again, I want to emphasize that science is not about the breakthroughs or the big moments. I mean, those are great, but it's the gradual progress made by thousands of people that really allow us to push our knowledge forward. So gradually pushing it forward, gradually moving it. To my knowledge, there hasn't been any major announcements about dark matter in the last month, although to be fair, I am actually a bit behind on my science papers. But that doesn't mean nothing interesting is happening. We're getting there, just slowly and steadily. You know, we're the tortoise racing against the rabbit. We're getting there. We'll get there eventually. I don't know who the rabbit is in this hypothetical scenario, just we'll get there. So yes, and also to be honest, I'm not keeping as up to date with dark matter research as I was in the past. Now that I've shifted my focus to gravitational waves, I am keeping more up to date with gravitational wave knowledge. Also, nothing major has happened there in the last month, but I am still more or less in touch with the dark matter side, with the dark side. I keep up to date with the dark side, and there hasn't been any major announcements in the last month to my knowledge. Also, this is something that would be a damn shame if Twitter goes. So there's a lot of reasons why I would be upset if we lose Twitter. And one of them is because Twitter gives me a way to see scientists talk about their work very easily. Oftentimes when there's a breakthrough or somebody has a cool paper, one of the authors will put a Twitter thread explaining their paper. And of course, that paper might not have passed peer review, it's the author's perspective, but it's always an interesting perspective. You just find like, hey, here's an author talking about their paper on Twitter, let me go read it. Just gives you another, their own take on that paper. And that's something that I really like and will honestly miss if Twitter goes away. Okay, I scrolled back too far and now there's a lot more comments coming in. Oh, I just saw a question by David Dunn that I missed. Do I have a favorite galaxy? Do I have a favorite galaxy? That is a good question. There are a lot of really, really, really pretty galaxies out there. And anytime we look at images from the telescopes, the galaxies are amazing. But I don't think I have a favorite other than the Milky Way itself, because this is the one we're in. This is the one we can study. This is the one where we can poke about and see what happens. We've explored a tiny, tiny part of our own galaxy. We've barely explored our own backyard. And our galaxy is so big and dramatic. And, you know, if you're in a place with no light pollution, you can look up and you can see the tail of the Milky Way, the arm of the Milky Way. And that is incredible. So my favorite galaxy, I'm going to be boring and say it's our own galaxy. It's the Milky Way, because other galaxies are pretty, but there's no place like home, right? So yeah, my favorite galaxy is the Milky Way. Going down, if the sun's gravity causes fusion, then inside a black hole must be infinite fusion, blown away by what could be inside. Now, sun's gravity causes fusion because you have the interplay of gravity pulling things inwards and pressure pushing things outwards. You have this nice interplay. You can you'll get a place that is very hot, very dense, with enough hydrogen, you can start fusion. However, in a black hole, you don't have the right conditions, to our knowledge, for fusion. The big thing here is that fusion would produce photons. So what would happen to the photons being produced inside a black hole where there is fusion, right? Because a star shines because it is producing photons via fusion, and these are going outwards. Inside, I'm just thinking on the spot here as what would happen. So I think it's not just the gravity you need in order to have fusion inside a star. You also need the right temperature, you need the right pressure. And while the gravity condition is fulfilled inside a black hole, I think the other conditions you need for fusion are not fulfilled. Again, we don't know what happens inside the black hole, but I don't think you have the right conditions to have fusion inside a black hole. You don't have the right temperature or the right pressure. Question from Scott here. If the plush toy, if my nice little black hole toy here, was an actual black hole, what would its mass be? Definitely less than the sun. A solar mass black hole is bigger, I believe. An Earth-size thing would be about 10 millimeters. So somewhere between the Earth and a star, I guess. Just pulling numbers out of my head randomly here, I would say that this is what? Let's say it's 25 centimeters across, so let's say a 10 centimeter radius. So that's 1 order of magnitude more than the Earth. So 1 order of magnitude more. The Schwarzschild radius changes directly proportional to the mass. So if mass increases by 1 order of magnitude, radius increases by 1 order of magnitude. So back of the calculation in the top of my mind, Earth is 10 to the 26 kilograms. So I would say 10 to the 27 kilograms. Does that make sense? No, it's one. Yes. Yes. So take about 10 Earths, collapse 10 Earths into a black hole. It will be approximately the size of this plushie, assuming my math pulled out of my brain makes sense there, which it may or may not be the case. But just pulling that out of my brain here, that's the number I came up with. So take 10 Earths, shrink them into a black hole. It will be about the size of a plushie. And I will actually calculate this later and give you the actual answer. But I'm going to say about 10 Earths is what you would need to make a black hole this size. So that's how heavy that would be if it was an actual black hole. But again, that was, as you saw, those were just numbers pulled out of my brain now. Going through the comments again. Could Einstein's equations not apply outside our galaxy? That is an excellent question. I'm assuming you mean Einstein's general relativity and not like things like the Planck formula. Yes, Einstein's equations, to the best of our knowledge, also apply outside of our galaxy. We've been able to see that using Einstein's general relativity, we can describe the overall large-scale structure of the universe. We can describe a lot of different things that are beyond our galaxy. However, there are some people asking the question of, are there regions of the universe where Einstein's general relativity breaks down? For an example, in a supervoid or a supercluster, so a region where you have a lot of matter, or a region where you have not much matter. People are working on that. So far, we have not found any deviations from Einstein's general relativity anywhere in the universe. The problem with being behind in the comments is that I'm no longer sure what these comments relate to. Like David Dunn just saying gravitational waves. Yes, I talked about gravitational waves, cool. Hoax object, I have no idea the context for that. I guess that's talking about favorite galaxy. Okay, it's hard to map out our galaxy, yes. I heard that the temperature of our sun isn't high enough to sustain fusion. Well, yeah. There is that fun thing here that in order to explain fusion within the sun, you actually need quantum tunneling. So, fun fact, there's a lot of quantum physics processes happening in the sun, and without those, you wouldn't have the necessary energy for the star to actually ignite. Fun. I'm not going to go into that now because that requires me reading up something before I talk about it. But yes, you basically need quantum effects to talk about you need quantum effects to talk about why the sun shines, which is cool. The bigger a black hole gets in terms of the event horizon, the less dense it is. Yes, because the density of an object goes like mass over volume, whereas the volume is radius to the 3, whereas the Schwarzschild radius, or the event horizon, goes directly like the mass. So the larger the mass, the larger the radius, the less dense it is, which is really, really cool when you think about it. That the more a black hole grows, the less dense it is. It's very cool. And yes, the back of the envelope calculation I did was for the event horizon. So in this picture, I am assuming that the event horizon starts here in my back of the envelope calculation of how much mass the black hole would have. Now, in reality, we know there's a gap between the accretion disk and the actual event horizon, so it would actually be a bit smaller. But we can brush that off as a statistical uncertainty in my measurements. 10 centimeter radius black hole is produced by 11.2 Earth masses. Okay, so my estimate of 10 Earth masses was pretty good. Thank you for that, David. I will measure the exact radius of my black hole. But I said 10 Earth masses, it's 11.2. I'll consider that as good enough because yeah. This is something that I think is amazing about being a scientist, that we're trained how to do these random calculations. Just pull numbers out of your brain that seem reasonable and try to reach an answer. And this is a skill that I think is really, really cool, and something that should be emphasized more, that we can actually do this, and we have to do this a lot in our work. And it's really fun. I actually did that recently. So I'm teaching a course this year. I'm teaching assistant on a course. I'm not the main lecturer. I'm teaching assistant on a course. I am the teaching assistant on a course, and it's Introduction to Quantum Physics, and it's really, really fun, and I get to chat to the students about quantum physics and all of the cool stuff, and give them cool examples. And I actually did a random exercise with them the other day of, if I give you the radius of the Earth, can you calculate the mass of all of the oceans of the planet together? Like, take all of the oceans of the planet, give me their mass, and all I'm giving you as a starting point is the radius of the Earth. And it's a really fun series of approximations and guesses you do, and you can actually get the answer just based on the radius of the Earth. You can calculate the approximate mass of the oceans, which is very cool. So yes, that's one of brain went on a tangent there, but it's very good to be able to do order of magnitude calculations and reasonable approximations. The teaching assistant thing is in English, definitely. There's no way I would be ready to do it in Finnish yet. So in the University of Helsinki, there's the bachelor's in physics is offered in both English and Finnish. The courses are very, very similar. Occasionally there's differences. Occasionally there's difference in what is offered, but the core subjects are offered in both languages. So people can get the bachelor in science in English or in Finnish. The quantum physics one that I'm doing, it's being offered in Finnish as well. And I'm staying away from the Finnish one. I'm offering the I'm taking part in the one that is offered in English, because I am definitely not yet good enough with my Finnish to even attempt something like that. My Finnish right now is good enough for ordering coffee and asking people if they speak English, which is and ordering cinnamon buns. And occasionally I can do things like tell you the day of the week or count to 10 if my mind is in it. And I know the word for shark in Finnish, which is hai. And I know like random words that are not helpful. But yes, teaching is done in English, and I'm very happy about that. Okay, going back to the comments. If one would want to learn about each force, is this a physics class, cosmology, other science? So if you want to learn about the 4 forces, this is something that you see in both general physics or in quantum physics. Or I think general physics is where you would start to cover it, because it's not just quantum physics. So it's something that, I would say a general physics class should cover the 4 forces. The first time I saw it was very, very late in my high school studies, just before going to university. But then I saw it properly in particle physics in university. But it's something that you can do also beyond particle physics. But yes, it's something that is taught a lot of times in general physics or in particle physics. Just checking that I caught up with all comments. I did indeed catch up with all comments. It's not how strong you start, it's how good you finish. Exactly. I will get there eventually. I don't plan on leaving this country anytime soon, so I have plenty of time to figure out my Finnish, and I do plan on getting there. I managed it with German, I'll manage it with Finnish as well. It will just take me a while. And what doesn't help with me learning Finnish here is that everyone, or almost everyone, speaks perfect English. So then I don't really need to use my Finnish because I speak English to everyone, which makes it harder for me to actually force myself to learn Finnish. But I do plan on changing that and focusing more on more on speaking to people in Finnish. That's like New Year's resolution, saying it out loud, manifesting, all of that nonsense. Next year, starting 2023, January 2023, I'm going to try to speak to more people in Finnish. New Year's resolution. There we go. I don't like New Year's resolutions. Like, why wait until the sun is in a specific spot or we're in a specific spot with respect to the sun to make life changes? Anyway, tangents. I like tangents. Keep going on those. So I think I've caught up with all comments, and we are almost at the 1 hour mark, and I am actually very surprised that my voice lasted the entire hour. I did not expect that, which means I am good to go back to work tomorrow, which is good. Not that I actually stopped working, but I should have done. But anyway, my voice is better, so that is good to know. So, cup of Finnish. I am not doing a stream in Finnish. That is not going to happen. I do have plans. Like we've said at some point, I would do a drunk cup of Cosmology. Just mentioned a karaoke cup of Cosmology. There's a high chance those two will go together. But yeah, a cup of Cosmology in Finnish, not going to happen anytime soon. Maybe I could just get two Finnish people to come and chat among themselves, talk about physics, and I just observe. But yes, I'm not going to do a cup of Cosmology in Finnish just yet. Language without slang is like a new language. Interesting to listen to. Yes. Yeah. Learning languages is fun. It's a good way to keep your brain active, but it's also difficult and challenging. But we'll get there eventually. Okay, so thank you everyone for joining. This has been great fun. Had a bunch of really cool questions. I like when I come without a topic and just like, it's always the thing of where are we going to go today? Karaoke in Finnish? Okay, so fun fact, Friday there was a Christmas party taking place in my campus. And for some reason there was karaoke taking place in the physics building. And I almost sang at karaoke. And then realized like this is very public in the building. This is where all of my work colleagues are. Definitely did not have enough alcohol for that. So, and there were songs in both English and Finnish. And somebody said to me at some point, why don't we sing a song in Finnish? My brain briefly considered it and it was like, hell no. No, not going to happen. Not going to happen anytime soon, at least. But yes, I can sing Baby Shark because I know the word for shark and I know the word for baby. So that's my level of Finnish. Anyway, what I was about to say here is I like when I come without a topic because then I come to the streamers. I have no idea where we're headed today. Let's see what happens, and then we get cool things like grand unified theories and all of these fun topics. I got to talk about gravitational waves a bit. I got to talk about dark matter. Very surprisingly, we had a whole stream without a single mention of my favorite topic, which obviously is completely unacceptable. I mean, how can we go a whole stream without even talking about the cosmic microwave background radiation? Made you all wait 59 minutes for it today, but it made an appearance at the end, just because. So yes, it's always great to come here and see which direction you're going to take me when I don't have a topic. It's always a fun adventure for me. So I like preparing topics, but I also like coming in like, let's see what people are going to throw at me today. It's fun. So thank you everyone for joining in, for humoring me, for asking me these questions, for following along. I know some of you have been following me for over 7 years now, and I really appreciate it. So it's great to see everybody come in. Yes, please do not do a drinking game where you drink anytime I talk about the CMB. I do not want to be responsible for that. Like, please don't do that. That would be bad for everyone involved. Okay, so CMB was debunked on Wednesday. What? No. I'm just ignoring that comment because that makes no sense. No. CMB is fine. CMB is good. Yes, squeeze the CMB in just last minute. So Thank you, everyone, for being here. This has been really, really good fun. It's great to chat to everyone. Great to have all your questions. If you haven't done so yet, please do like the video, leave a comment, subscribe, do all of the YouTube things. It really does help. If you want a say in how to receive future updates about Cup of Cosmology, you can head over to Twitter, check out my pinned post. There is a poll there. You can tell me where you want Cup of Cosmology updates to move to if Twitter stops going. Macedon is not an option, but potentially a Discord server might happen in the future. So, I do appreciate all of the comments and everyone who's made me laugh here. Thank you. It's always great to have you. I should be online again next Sunday, same time as always. That's 7 p.m. Central European Summer Time, 1 p.m. if you're on the East Coast, 10 a.m. if you're on the West Coast. And there's a time zone converter on cupofcosmology.com, so you can figure it out in your own time zone. So I hope to see everybody next Sunday, same time as today. And I hope in the meantime, you all stay safe and take care of each other.